Hey, so today we're going to talk about 11.7 through 11.16, sort of the end of the chapter. And what we're going to start to talk about is wave motion and how waves can be modeled and represented a couple of different ways. There are two different main types of waves, but all waves have that periodic behavior. We're looking for highs and lows, that type of behavior. An example you can think of is swinging a rope, and as you swing it up and down, you can create the part. If you look at this drawing right here, it's a really good model of the fact that a single spot on the rope is actually only moving up and down. That individual particle or that piece, it's moving up and down, but a signal, okay, the wave itself is traveling horizontally through the medium or through the space. And so understanding that there's those different types of motion inside of the wave, that's a really interesting and important piece when we talk about how we manage and understand waves themselves. When we talk about simple harmonic motion and waves, we have that up and down at a repeated interval. And let's talk about some of the characteristics of a wave. One, we know the amplitude is from the center line up or from the center line down. We'll call them crests and troughs or nodes and antinodes. Talk about that more in chapter 12. But this other piece that we want to talk about is what's called a wavelength. And we use this Greek letter lambda right here to represent a wavelength. And that's, think of it like the period is what we traditionally would call it. It's from a point to the same point in the cycle. But period, okay, period is about time. Hence why we measure it in seconds and we use a capital T. Wavelength is about distance. It's how long is this wave physically, and we measure that in meters. And so whereas we talked about period being a time, wavelength is a distance. It turns out that there is a connection between wavelength and frequency though. And that's where we get some really cool things to come out of this. And it comes out of this formula right here that says for all sinusoidal waves, the velocity of a wave is equal to the wavelength times the frequency. Now that actually turns out to be a pretty fundamental concept. So what that allows us to do is if we know the velocity of a wave and we know its frequency, we can find its wavelength, or we know its wavelength, we can find its frequency. And that does a lot for helping us understand things like how waves interact with one another. Now, there's two different types of waves. There's what we call a transverse and what's called longitudinal. Transverse is like the traditional sine wave look. It looks like a sine wave. And you can see the up and down movement as it goes transverse, or transverses its axis, crosses its axis. The other type is a compression wave. We call it a longitudinal wave. And you can see these spots of high density or high pressure, and you can see these spots where it's been spread out. If you were to map those out, high point, low point, high point, low point, you would still be able to find that sinusoidal or simple harmonic motion inside the wave. So they're both waves, they both have similar characteristics. They're just, one is, again, across the axis and one is along the axis. When we talk about transverse waves, or longitudinal waves, see there's our image of our compression matching a sinusoidal wave. When it comes to finding the speed at which, say, sound travels through a material, because sound is a compression wave, which makes it longitudinal. When we talk about these longitudinal waves, they depend on what material they're passing through. And so we have these two different equations that we're going to use to find out how well does my voice travel through water, how fast does it travel through metal, those different types of things. We want to travel sound through something. It's going to depend on what's called its modulus. And there are two different types of modulus. There's an elastic modulus, okay, where we're talking about a solid object. And then there's what's called the bulk modulus for a fluid, some sort of gas or liquid. Typically we consider that a fluid. Now these two values, E and, so this formula here, we've got some information here. Okay, if we're looking at E and B, those can be found on page 238, and that's in chapter 9. So if you're looking for that table with E and B, you want to say how fast does sound travel through water? Well, that would first off be a liquid or gas, so we'd use this formula with B instead of E, and we'd have to go to page 238 to find that. The other value you're going to need is the density. Now we did densities before, that's on page 256. Again, if you don't know where that is in the book, that's in chapter 10 if you're looking online. But those are the pages you're going to have to go to find these values. But that will allow you to calculate. The more dense a material is, if you look at this, it's actually going to slow some of the, as the density increases, you're going to see that fraction decrease in value. So the velocity actually slows down. But depending on the structure of the material, it can actually travel faster. So there's a little bit of question as to how flexible is the material. Does it absorb sound? Does it transfer sound really well? And so we can see certain materials it travels faster through than others. Let's clean that up real quick. All right, so we've got different ways to calculate velocity. We can calculate the velocity of a wave by the wavelength times the frequency, or if we know it's a longitudinal wave, like a sound wave, we can check it using these two formulas here. One of the things that we have to realize is that when we do things like echolocation, radar, stuff like that, we will send, I'm just trying to see if there's anything else I need to grab out of the book here real quick, and I don't know that there is, other than how waves interact with each other. No, I think we're pretty good there. But when you're dealing with things like echolocation, sound waves bouncing back at you, what you have to realize in all of this is that if I make a noise right here, it bounces out, right? I could figure out the velocity of the wave. Let's say it's 340 meters per second. That's roughly the speed of sound in air. It's traveling that fast. It hits a hard object and then it bounces back, right? And when it gets back to me, I stop my stopwatch. Something you have to fundamentally understand about the distance we just had the sound travel is that it was there and back. So whenever you're looking at the time for a sound wave to get somewhere and back, it's going to be double the distance that we want to actually measure. So that's something to think about. When you think about the problems that you're given, always consider, well, how far is it actually traveling? Hopefully that's enough to kind of help you understand where the formulas are coming from, where to find stuff in the book. It is a book-dependent assignment when you look at the bulk modulus and Young's modulus. You have to look at those E and B and the densities. Those are all going to come out of the book. So feel free to go there and use as much as you need. All right, see you in class.